Hey. Hi. Um, excuse me. We're going to do reaction mechanisms, okay? Probably we'll finish up chemical kinetics right now, all right? Reaction mechanisms, how to determine if a mechanism is acceptable. That requires writing a rate law from a proposed mechanism. Learning about intermediates and catalysts, how to identify them. All right. Should have hopefully, I think I attached a sheet of paper for you. It'll look like that. That's about to disappear though. And we will be referencing that throughout some of this class period, okay? So you will call this, once again, reaction mechanisms. All right, mechanisms. What is a reaction mechanism? Well, guys, it is a series of proposed steps. All right, showing how we get from reactants to products. Whoa, I don't know how that happened. Showing how reactants form products. All right, you will not have to write a reaction mechanism, but you will have to look at one and you will have to determine if it is acceptable or not. And you will have to be able to identify intermediates. The proposed steps are elementary steps. All right, and you just looked at elementary steps. Remember that you can get a rate law from an elementary step by using the reactants only, and you do not have to pay attention to the products. We will be doing that. All right, we will see intermediates and catalysts and need to be able to identify if they are present, and if so, who are they? What are they? Rather, an intermediate is first produced, so it is a product first, and then consumed, so it is a reactant second by a reaction. It will not be present in the reactants or the products of the overall reaction because it will be canceled out. It'll be a product first and a reactant second. A catalyst does not participate in the reaction, does not participate. It is simply there to offer a alternate pathway, and that alternate pathway has a lower activation energy. All right. The catalyst is also not in the overall reaction. I have seen them in rate laws. And it is a reactant first, and it is a product second, and it will cancel out. Okay. We are then going to, once we look at identifying which is which, we're going to do all this at once in a second, sorry. We're going to determine if a proposed mechanism is acceptable. A proposed mechanisms is acceptable, because so I'll write mechanisms are acceptable if, okay, and we're going to see that two requirements are going to have to be satisfied, and that if is one, the overall reaction matches the actual, is the same as, if you like that better, the actual reaction. You will be given the actual reaction. If they're the same, that's one check. We also need another check. That second check comes when the rate law from slow step matches, is the same as the experimentally determined rate law. All right. Now let's look at what Miss Murphy is talking about. Ideally, the rate law from the slow step, right? Let me go ahead and give you your notes because we're going to apply. This is the rate determining step. Think about it. You are going through a process. You're in the kitchen making a pie. What determines the actual rate is that slowest step, whatever takes the longest. So the slow step is the rate determining step, and it will therefore determine the rate law. We won't treat it like it is an elementary step. So we'll pay attention to reactants only, and we will not be concerned with our products. And ideally, let's write ideally, the rate law does not contain an intermediate. Rate law does not contain an intermediate. So we're about to apply all of this stuff, an intermediate, and we're going to do that in that worksheet that I have attached to this. So those are your notes. Let's apply them. You can pause at any time. All right. This is the worksheet that I usually give to my students in class, but this year's different. So we're going to go through some of this together. Okay. Now, remember we looked at elementary steps. And if we combine those elementary steps, we have a reaction mechanism. Remember, elementary steps could be unimolecular, bi, or termolecular. And remember that we could write a rate law based on the reactants in an elementary step, right? Remember that? You just did that. Well, we will apply that here, okay? So what we have here is we've got the kinetics. Well, that's just everything I was just saying. The slowest step will determine the overall rate of the reaction and is called the rate determining step. The sum of the elementary steps must give the overall balanced equation. They must also explain the experimentally determined rate law. The kinetics of the reaction 2x plus y yields z was studied, and the results are as follows. Deduce the rate law, including the value of K with units. So I would like you to just pause and do that. And you're going to see that now you're coming back. The rate is equal to K Y. All right. Make sure I'm right there because I just did that. Yep, K Y. And what are the units of K? I want you, if you did not write it, to pause. I want you to think, what are the units of K? If you don't know it, listen to me. The overall reaction order is 1. So get that moles per liter second. Get rid of one of those. And we're down to 0. So the units for K are per our unit time, which is seconds here. That is a per second. Either one of those should work. All right, done. If you have questions about that, you can ask me later. Now, B, the following 3 mechanisms have been proposed. The species M and N are called intermediates. They're formed in early steps and consumed in later steps. What is the overall order of, or what is the overall reaction for each mechanism? Okay, let's do that. Let's look at the first one. And I see that M cancels because it is present on both sides of the reaction. And it is first a product and then a reactant. So it is an intermediate. You need to be able to identify that. And what I'm left over with are 2 x's. So that would be 2x plus y yields z. Let's do that for the next one. And again, I want you to ask yourself, is there an intermediate? If so, cross it off. And then tell me what's left over. And what you should have, and pause if you need to, So x plus y yields z. And yes, you do have an intermediate. It is M again, intermediate. Okay, it is first a product and then a reactant. Go ahead and move to the last one. Pause, cross off anything that needs to be crossed off, and then get the overall reaction. And you should have 2x plus y yields z. Okay. Once again, we did have M as an intermediate. We also had N as an intermediate. Okay, let's go back up. What is the overall reaction for each mechanism? We just wrote that. What is the molecularity of each step? Well, this has two reactants. It's bimolecular, bi, uni, uni, bi. Okay, thank you. What is the rate law derived from each? Okay. Rate law derived from each. So make sure you pay attention here. I'm going to get rid of that stuff there. Okay. So I need the rate law. We said that the slow step will determine the rate law. So I'm going to go to my slow step in each situation. And I'm going to say that according to my slow step, the elementary step that is identified as my slow step, the rate is equal to K. Now I'm simply going to look at my reactants, and I have 1x, so it'll be x raised to the 1, and 1y, so it'll be y raised to the 1. Okay. According to mechanism 1, that's the rate law. According to mechanism 2, right, I need to go back to the slow step. And I'm always going to write rate. And we're always write equals to K. And then I'm going to see that, look at the reactants. There's only one Y. So that's it, right? Okay. Now we're going to go to our last mechanism, go to the slow step. And according to the slow step, the rate, according to the slow step, the rate is equal to K Y. Okay. Okay. Let's go back up to our question here. What is the rate law derived from each? Well, we just did that. We just looked at the slow step and looked at the reactants. Which mechanism is consistent with the rate law from part A? Well, the rate law from part A has this reaction. So we need to find the overall that is 2x plus y yields z. Well, this is 2x plus y yields z. This is 2x plus y yields z. This here is not. So this mechanism is not acceptable because the overall, not acceptable. Why? Because the overall reaction is not the same as the actual reaction. Okay, so that mechanism is not going to work. Now, we've got two options right now. It could be mechanism 1 because the overall is the same, or mechanism 2 because the overall is the same. Now, if we look up, remember there's two requirements. The overall has to be the same. The other requirement, if you remember, was that the experimentally determined rate law is consistent with the rate law from the mechanism. That one is not consistent, right? That is not consistent. The second one is consistent, but it's not an option because the overall was not the same. So that one was already out. And what we see here is this rate law which is provided by the slow step in this mechanism, is the same as the rate law that was experimentally determined by using the initial rates method. Remember, rate laws can only be experimentally determined. This mechanism's rate law happens to be the same as what was experimentally determined. The mechanism has an overall that is the same. So for both reasons are satisfied, mechanism 3 is an acceptable mechanism. This is an acceptable mechanism because the overall reaction is the same as the actual reaction, and the rate law of or from the slow step matches the experimentally determined rate law. Okay, now I'm going to actually, guys, we could finish this with one more thing. Be done. Okay, so let's go ahead and take that one step further. Now let's look here. There are often equilibrium steps in mechanisms. Okay, that's what's happening right here. We will usually assume that they are not rate limiting, that they're not the slow step. Okay, don't worry about it. That means it's not the slow step. It won't determine your rate law. The concentration of the species involved can be determined by setting up the equilibrium expression. So let's just look at this. Determine the overall reaction. Okay, we don't need that. Anything going to cancel? Let's see. This is an intermediate. It is produced and then consumed. This is an intermediate. It is produced and then consumed. So you go ahead and pause, answer. I should have let you do that. And then start, obviously, we've got 2NO, or do however you want to do it, 2H2, I'm just giving you options, N2 plus 2H2O. It's easy. All right. Are there are there? Yes, there are. Yes. N2O2 and N2O. We didn't ask, but determine the rate law. Any intermediates may not appear in rate laws. Okay, so this is a new thing to learn, guys. The last thing, according to the slow step, all right, the rate is equal to K. Let's look at our reactants. Even though it's crossed out, we have to put it in here. N2O2, H2. All right, we just write it down and let the stoichiometry determine the order. That's the only time you can do that. Now, this is an intermediate, is an intermediate. Therefore, try to redefine with equilibrium step. All right, this is easy, but just hang in there with me. Okay, so let's clean this guy up. The problem is this guy here is in our rate law, and it's an intermediate. What's always going to happen is that intermediate is going to be a member of your equilibrium step, which will always be the first fast step, okay? So problem is we have an intermediate in our rate law. Our rate law right now, according to our slow step, is N2O2, H2. As we said, we must redefine this. Okay, so this is always the thing we're going to do. We're going to go to our equilibrium step. The deal with equilibrium is that the rate of the forward is equal to the rate of the reverse. And by forward and reverse, I mean reaction. We're going forward, reactants make products at a rate, and products make reactants. When that rate is equal, the rate is equal, we are at equilibrium. Now, let me move my face over here. Okay, so listen to me here. If I look at this in the forward direction, okay, then this is my reactant. So therefore, in the forward direction, rate forward equals K NO squared. Okay. And rate reverse means that, listen to me here, if I'm going in the reverse direction, then this is my reactance. So it's K and my reactant is into O2. Okay? Now, now listen, remember this, hold on, stay with me, we're almost there. Rate of the forward equals rate reverse. Well, rate of forward is K NO squared, and that's rate of the reverse, which is K into O2, right? I just made this equal to this because one is the forward and one is the reverse. So I set them equal to each other. Now remember, the goal was to redefine, let me go here, because we were going to redefine this guy because it was an intermediate and we don't want it in our rate law. Well, he's right here. So if I can rearrange this equation to solve for N2O2, then I can plug that in, all right? So let's do some algebra, and let's see that N2O2 is equal to K. We'll call this is K forward, this is K reverse, so K forward over K reverse time, oops, sorry, I was just looking at what I needed to do actually. We're gonna pull him down, and that would be NO squared. So I now know that the concentration of N2O2 is equal to a new K, and kind of go like that, times NO squared. And I can take this here, which is this, and plug it in to this. And what do I have? I have the rate equals K NO, and you can just, don't even worry about the K's. It's really like a K, a new K. You don't even have to worry about it. We have a new K. Okay. Okay. Squared. And don't forget the other part, we still have that H2 in there. H2. So what we have down here is this got turned into rate equals K. We redefined N2O2 as being, oops, NO squared, which is not an intermediate, and we had to keep our H2 in here. So that is our answer. And that's what happens when you have an intermediate in the slow step. What is the overall order of the reactions? Well, that would be a third order because we have a second order plus a first order, 2 plus 1, third order. Overall, oops, shoot. 2. Oh my gosh, y'all, I keep doing the same thing. 2 Let's get rid of that right there. Okay. And then what is the molecularity of the rate determining step? Well, let's look up here. The rate determining step was the slow step. It was bimolecular. I don't see why that's very important. Okay. Write the overall reaction. And what I want you to tell me is, what are your intermediates? What are your catalysts? What cancels? All right, Mn3 plus is an intermediate. Okay. Mn4 plus is an intermediate. Now I want you to look and see if you can find a catalyst. Catalyst is there in the beginning and it's there at the end. Okay, so you should right now hopefully be seeing this guy here. So that's what a catalyst looks like. It is first a reactant and then a product. So Mn2 plus is a catalyst. And we see now that these are our reactants and these are our products. We could write those in there, okay? Assuming that the catalyst is involved in the rate determining step, what is the rate law for this reaction? Well, the catalyst we said is in step 1, right? So we would write the rate law for this elementary step. Rate equals K CE 4 plus and Mn 2 plus. Why is the uncatalyzed reaction so slow? What is the overall reaction? CE 4 plus 2 plus EL plus yields 2 CE 3 plus TL 3 plus. Well, it is trimolecular or termolecular, right? Therefore, and I'm not going to write this, therefore there's a lot of stuff that has to happen for that step to have effective collisions, right? It's already got a high activation energy because it's a slow step. It's termolecular. There's 3 particles that have to collide with the correct collisions in order for those collisions to be effective. So the higher the molecularity, the less likelihood of effective collisions. If that, as the more things that have to combine in the correct orientation with the correct energy, the less likely that is to happen. So that's what they're talking about there. Under certain conditions, it is found to be second order in NO and first order in Cl. Given the following mechanism, what are the relative rates of the 2 elementary steps under these conditions? Well, if it is found to be second order in NO and first order in Cl2, what is your rate law? Second order NO is NO squared and first order Cl2. Okay, well, we've got to take this and now figure out which one of these must be the slow step. Okay, well, let's get the rate laws. Here, let's at least start at the top. All right, let's clean this up. Rate, if this was the slow step, then the rate would be equal to K NO Cl2. Well, that's not the same as that. So this should not be our slow step, excuse me. Okay, now let's look at our second one. We have rate equals K NOCl2 NO. Okay, well, that doesn't work either, but this is an intermediate. So we need to redefine and plug in for it. So let's do what we said again and do it more quickly. Let's go to our equilibrium step. Remember, rate forward equals rate reverse. In the forward direction, let me get a different color. In the forward direction, these are my reactants. So K NOCl2 is equal to, that's the forward K, the reverse K. Remember, when we go in reverse, that these are the reactants. So that's K reverse NOCl2. Let's rearrange this equation so that it says is solved for this guy, so that we have NOCl2 equals, now let's get this down here, right? So we have KF over KR, which we'll just call K prime or something. And then that's it. That's it. We're just going to go like this and go like this. So we now know that NOCl2 equals a new K times NO and Cl2. So if we plug this in here, we have rate. Let me scoot that over a little bit. Oops, I want to get rid of all that. We have, right, so we're going to plug that in here. Now we've got rate equals our new K. Don't worry about that. NOCl2 is now NOCl2, and then we still have this NO. So let's simplify that. Rate equals our new K, NO squared Cl2. Well, the question was, we needed to know which of these steps was consistent with our experimentally determined rate law. Remember, under certain conditions, the reaction was found to be this. So experimentally, this is the rate law. And we see that the slow step gives us a rate law that is the same as the experimentally determined rate law. Therefore, step 2 is the answer. We had to redefine for our intermediate. Man, maybe you should finish this yourself. Why don't y'all finish this yourself? Finish this yourself. Okay, we're gonna go ahead and go here. All right? Ooh, should we do it together? Finish it yourself. Bring it to class. All right? Do that. I'll see you. Stop. Bye.